Alright students, in this video we're going to talk about solutions and different ways of measuring concentrations of solutions. Solutions are actually in a homogeneous mixture, and if you guys recall, homogeneous mixtures have an even compositions of at least more than one type of materials. You could have two materials, three materials, or more than three types of different materials. As an example, air is actually in a homogeneous mixture because air is made of the nitrogen gas, the oxygen gas, the carbon dioxide gas, and there are tons of other gases in small concentrations, and they're all evenly mixed up. As a result, it's in a homogeneous mixture, and it's also in a solution. Another example would have been the lemonade. In lemonade, we have the water, we have citric acid, and we got the salt, and probably some other flavors in there, and they're all evenly mixed up. So that's an example of an homogeneous mixture and as a result of solutions. Now, in this chapters, to keep things simple, we're going to be talking about solutions that are actually made of only two types of materials. We don't want to consider more than two types of materials to just keep things simple. And those two materials, one of them would be called a solute and the other one would be called a solvent. Now, it's very important to be able to identify what the solute is and what the solvent is. The easiest way to identify the solute and the solvent in the solution, the solute is going to be present in least in amount, and your solvent is going to be present most in amount. If I take an example, I talk about maybe sugar solution. In a sugar solution, I know I'll have sugar in there and I'll also have water in there. Sugar is going to be less in amount, and since sugar is going to be less in amount, it's going to be considered the solute, and your water would be considered the solvent. Now, when we talk about how can we measure the amount of solute in the given solution or the solvents, we're talking about different ways of measuring concentrations, and there are actually multiple ways of measuring concentrations. And at the end of the day, we may not use all of them very often. There's a couple of them that's used a lot, but that doesn't necessarily mean you don't use other ways of measuring concentrations at all. So let's start with the mass percent. In case of mass percent or the weight percent, you're actually going to be measuring the mass of the solute and the mass of the solutions. Now, the units could be either grams or kilograms or anything basically, as long as you keep both of those units to be the same. The definition of mass percent is going to be the mass of the solute divided by the mass of the solution. Now, this is something you guys have to make sure you keep in mind. It's the solution in the denominator, not the solvent. If you guys recall the definition of percent, it's always going to be the part divided by the whole thing times 100. So we're doing exactly the same thing when we're trying to figure out the percent solute in there. We're doing the mass of solute divided by the mass of solution times 100. Like I said, you could use any units for the measurement of the mass as long as you keep those to be the same. So I can have grams for the solute and grams for the solutions, or I could have kilograms for both of those. As long as you're consistent, it's fine. So that's one way of measuring the concentrations when you weighing out your solute and your solution. Now, let's suppose you have the liquids for both your solute and your solution. So you could measure the percentage, or you can measure the concentration in that particular case in terms of volume percent. In volume percent, the units could be used as milliliters or liters or centimeters cubed, as long as they are the same. The definition of volume percent would be the volume of solute divided by the volume of solution. Volume of solution. And both of these going to be measured in the same units, and it doesn't matter what unit you use. You could use either milliliters for both of those or liters for both of those. As long as you're consistent, it's fine, and obviously times 100, so that gives you the volume percent. And a typical example of volume percent concentration used is in case of consuming alcohols. For example, beer is what, like 4 to 8% by volume alcohol. So that means in every, if it's 5%, let's say 5% alcohol, that means in every 100 milliliters of solution, I would have only 5 milliliters of actual alcohol. So that's going to be your volume percent. Now, sometimes you also measure these concentrations in terms of mass volume percent, and this is where you have to be a little bit careful with the units. This technically means you're measuring the mass of the solute, but when it comes to solution, you actually measuring the volume of the solution. So that's why it's called a mass volume percent. And the mass of the solid is going to be measured in the grams, and the volume of the solution is going to be measured in milliliters. So this is where you have to be careful with the units. You can't use other units. You just use grams for the solids and milliliters for the solutions times 100, and that gives you the mass volume percent. Okay, well, those three ways of measuring concentrations are actually not very commonly used in chemistry. The most commonly used units of most commonly way of measuring concentration that's used in chemistry is actually molarity. Okay, so the molarity has a symbol of uppercase M, and the definition of molarity is the moles of a solute divided by the liters of solution. So your solution must be in liters for that case. And sometimes you're going to be seeing this molarity written as moles divided by liters. So keep that in mind. It's one of the most common ways of measuring the concentrations in chemistry. And now a lot of time you're not going to be given the moles of the solute. You may be given the grams of solute, and if you're given the grams of solute, you actually have to first convert the grams of solute into the moles of solute before you can actually figure out the molarity. The other uh, unit for other way of measuring the concentration is called molality. It's slightly different than the molarity. The molality is going to be the moles of the solute divided by the kilograms of the solvent. Now, this is I want to make sure that you guys see the difference here. So far, all the concentrations we have been talking about, they were measured in terms of solutions. In the denominator, you always had the solutions, whether it was the mass or the volume or the liters, but molality is the only ways of concentrations where you actually focus on the solvent. You don't really focus on the solution. So keep that in mind. And that solvent is going to be actually measured in kilograms, not in terms of the volume. Okay, well, Then you may also see the mole fraction. The symbol for mole fraction is this Greek letter. It looks like X. And mole fraction, just like the name says, fraction is just the fractions of the moles. So if I have two compounds in the solution, let's say compound A and compound B made up a solution. So I can calculate the mole fraction of A. The mole fraction of A is going to be the moles of A divided by the total moles, which is going to be the moles of A plus the moles of B. If you have more than two types of compounds, then you would add up the moles of the third compound in there as well. Similarly, I can also calculate the mole fraction of B. All right, so mole fraction of B is going to be the moles of B divided by moles of A plus moles of B. All right, now the mole fraction is always going to be equal, the sum of mole fractions is always going to be equal to 1. So if you know the mole fraction for one compound, you can easily figure out the mole fraction of the second compound, which means if I know the mole fraction of A, to calculate the mole fraction of B, I would do 1 minus the mole fraction of A. Okay, so then if you have a very, very small amount of solute present in the solution, then we can use a smaller concentration terms, and one of them is called parts per million. The definition of parts per million is the mass of solute divided by the mass of solution, and you want to make sure you keep the units for both of those to be the same. I can say the solute is measured in grams, so your solution is also going to be measured in grams times 10 to the 6. So remember, the percentages were timed by 100 because it's a percent. Now we're talking about million, so you multiply that by 10 to the 6. Um, when do we really use parts per million? Remember, we have small time heavy metals in drinking water, and their concentrations are very small. So to measure the concentrations of those heavy metals in drinking waters, we use either ppm or sometimes even ppb. And I didn't really write down the ppb here, but I want to mention what ppb is. Ppb is actually parts per billion. So the difference would have been you still have the mass of the solute divided by the mass of solution. Both of those needs to be measured in the same units times 10 to the 9, because remember, in billion you have 9 zeros, so it's even a smaller way of measuring concentrations. And then you can also have PPT, which is parts per trillion, but if you understand how you calculate the problems using parts per million, you should not have any problems doing ppb or even ppt. Now, to wrap up, I want to actually do this question, and that actually talks about the mass percent, mass volume percent, molarity, and the molality. And let's look at this question briefly. It says a solution is made by mixing 20 grams of NaCl in 100 milliliters of water. The density of the resulting solution. So this density is actually after you have mixed the water and the sodium chloride in there. And you have to find the mass percent, the mass volume percent, the molarity, and the molality. Okay, so before we actually come down to find the mass percent, let me just kind of go back and be able to identify what the solute is, what the solvent is, and what the mass going to be for the solution. So this NaCl is actually going to be your solute because it's 20 grams present, and we have 100 milliliters of water, so that's going to be your solvent. So I'm going to say, okay, this is going to be my solute, and 100 grams, 100 milliliters of water is going to be my solvent. If I have 100 milliliters of water, how much is that going to be in grams? Well, that's also going to be 100 grams of water because remember the density of water is 1 grams per milliliters. This is something you should memorize. You have to memorize a lot of stuff about water, and density is one of them. If you have 100 milliliters of water, that literally means it's 100 grams of water. Okay, now I know my solute, I know my solvent. Now let's figure out the mass percent. Now if you recall the definition of mass percent, I would be talking about the grams of solute, which in this case it's the NaCl, divided by the grams of solution times 100. Okay, well, do I know the mass of my solute? Yes, I do. The solute is NaCl and it's 20 grams of NaCl. So I'll go ahead and write down 20 grams of NaCl in there. And the next, do I know the grams of solution? Is that going to be 100 grams? Actually, no, because remember, 100 grams is the water, which is the solvent, and your solution is going to be the sum of your solute and the solvent. So this is a very common mistake students makes all the time. They would write down 100 here, but it's not going to be actually 100. It's going to be 100 plus 20. It's going to be 120 grams and then times 100. So at the end of the day, we got 20 divided by 120 times 100, and we can just do this math, and it comes out to be, so 20 times 100 divided by 120 is going to give you 16.67%. 16.67% NaCl by mass. That's how you write it down. So this tells you you're measuring the percentage of NaCl in this particular solution in terms of the mass. So it's going to be 16.6%. I can also say if I look at 100 grams of the solution, now we're talking about the solution. If I look at 100 grams of the solution, it would have 16.67 grams of NaCl by mass. All right. Well, let's look at mass volume percent. So to figure out the mass volume percent, the definition would have been grams of the solute divided by the milliliters of the solution times 100. Now, do I know the grams of solute? Yes, I know the grams of solute, which is 20 grams. Do I know the milliliters of solution? Well, the answer is no. The 100 milliliters of water, that's actually the solvent. I do not know how many milliliters of the solutions I have. However, I do know I have 120 grams of the solution. Because remember, if you add 100 grams of water and 20 grams of NaCl, it's going to make 120 grams of solution. Can I figure out how much that going to be in milliliters? Of course you can. That's why they have given you the density of the resulting solution, which is 1.10. So I can use the density as my conversion factor here. So I'm trying to figure out the milliliters of solution. So I'll put that on the top. And I'll put down the grams on the bottom. So grams of solution. And we are told that the density of solution is 1.10 grams per milliliters. So I can go ahead and do 120 divided by 1.10 to figure out the volume of the solution, and it comes out to be 109.1 milliliters of solution. Okay, if you don't want to do the dimension analysis to find out the milliliters of solution, you can also use the definition of density. Remember, the density is the mass divided by the volume. All right, and we knew the density that was given us in the question, that was 1.11. 1.1 rather, and then we knew the mass of the solution, and from there you could calculate the volume, and that's exactly what we did down there, but just we did that in terms of dimension analysis. So that's going to be 109.1 milliliters of solution. Okay, well, we know now the mass of the solution, mass of the solute, and we also know the milliliters of the solution. So let's just go ahead and plug it out. So we have 20 grams of NaCl divided by 109.1 milliliters of solution times 100. When we do this math, so a lot of time the mass volume percent and mass percent, they're close to one another. They're not going to be exactly the same unless it's a very dilute solution. If it's a very dilute solution, then the density is usually considered to be 1, and that's when your mass volume percent and your mass percent would be the same. Otherwise, they're going to be slightly different. So your mass volume percent comes out to be 18.33%. You can say NaCl, and you can say by mass volume. Okay, so the mass percent was 16.67. Your mass volume percent is 18.33%. They're fairly close to one another, but they're not exactly the same. And like I said, they would be the same if the density of the resulting solution was 1. Okay, moving along, let's try to figure out the molarity. The definition of molarity is going to be the moles of NaCl divided by the liters of solution. Do I know the liters of solution? Well, I do know the milliliters of solution. So we have 109.1 milliliters of the solution. And from here, we can certainly calculate how many liters of that solution going to be. So recall the relation between the milliliters and the liters. So since we're trying to find the liters, I want to put the liters on the top, so liters of solution on the top, and I want to get rid of the milliliters, so I'll put milliliters on the bottom. And what's the relation between the liters and milliliters? Well, 1 liter is actually 1,000 milliliters. So you do the math here, milliliters of solutions cancels out, and at the end of the day you'll have only liters of the solution. 109.1 divided by 1,000 is going to be 0.1091 liters of solution. So now I have the liters of the solution. I do not have the moles of NaCl. Okay, so we need to go back and figure out the moles of NaCl. What we know is the grams of NaCl. If I'm given 20.0 grams of NaCl, how do I find the moles of NaCl? So this is where you have to go back and recall your mole concept. In mole concept, you learned how you calculate the mass from the moles and vice versa. And anytime you're going from mass to moles or reverse, you either using the atomic mass or the molar mass. So in this particular case, we're going from the mass to the moles. So I'll go ahead and write down moles on the top. So I'll have moles of NaCl, and I'll write down grams of NaCl on the bottom. Okay, well, one goes with the moles and one number goes with the grams. That's going to be your molar mass of NaCl, or the formula mass. The formula mass of NaCl is going to be the addition of the atomic mass of sodium. All right, so sodium's atomic mass is about 22.99, and plus the atomic mass of chlorine, which is 35.45. And when you add this up, it comes out to be 58.5. Close to it. Okay, so then your grams of NaCl cancels out, and you can do your math by doing 20 divided by 58.5, and that gives you 0.342. It's going to be 0.342 moles of NaCl. Well, now I have both of those things. I have the moles of NaCl and I got the liters of solutions. That means I can go ahead and calculate the molarity. So I can just kind of go back there and plug those numbers in. So the moles of solution is going to be 0.342 moles and divided by 0.1091 liters of solution. So when we do this math, it comes out to be 0.342 divided by 0.1091 liters is going to be 3.13 molar. So 3.13 is going to be an uppercase M. That's how you write it. The uppercase M can also be written as moles over liters. But anytime you see an uppercase M, that means we're talking about the molarity. So the molarity of this particular solution is 3.13. Okay, well, let's talk about how you're going to be calculating the molality here. So the molality, which is going to be the lowercase m, is actually going to be the moles of NaCl divided by the kilograms of solvent. We already know the moles of NaCl. We actually calculated the moles of NaCl when we were trying to find the molarity. So that's going to be already known by now. The kilograms of solvent. So what solvent we used? So if you go back into the question, we used 100 milliliters of water, and that was our solvent. And 100 milliliters of water was actually equal to 100 grams of water because the density of water is 1. So we know our solvent is actually 100 grams of H2O. Well, remember, I need to calculate this into kilograms, not in grams. So I can go ahead and convert this grams to the kilograms. And since we're trying to find the kilograms, I'll have the kilograms on the top, so kilograms of the water here, divided by the grams of water because we're trying to get rid of the grams. And then we just plug in the numbers. So recall the relation between the kilograms or the grams. Remember, the kilo is just a prefix, which is 1,000. So 1 kilogram is actually going to be equal to 1,000 grams. So 100 divided by 1,000, it's actually going to be equal to 0.1 kilograms of water. Okay, well, I do know both of these unknowns now. I know the moles of NaCl, and I do know the kilograms of solvent as well. So the moles of NaCl were calculated to be 0.342, and the kilograms of the solvent is going to be 0.1 kilograms of water. So when you do this math, it comes out to be 3.42 moles divided by the kilograms. And this moles divided by kilograms can also be written as a lowercase l. And this lowercase l is also called molal. So it's M-O-L-A-L. And if I go back to the molarity, this uppercase M is also called molar. So it's M-O-L-A-R. So know the difference between the uppercase M and the lowercase m. You can see how the molality and the molarity are actually close to one another. The molarity is 3.13 and the molality is 3.42, just like the mass percent and the mass volume percent. The molarity and your molality would also be the same if the density of the resulting solution was 1. Or another way of saying, if the solution is dilute enough, that's when your molarity and the molality are the same. If the solution is not dilute, the molarities and the molarity is going to be actually close to one another, but not going to be the same. All right, hope it helps, and I'll post some more questions soon.